Dear students, today I want to discuss the properties of fluids, giving importance to Bernoulli's theorem and viscosity. At first, we can go through the characteristics of an ideal fluid. The fluid is incompressible, and keep in mind the density of the fluid remains constant, and the fluid is non-viscous. There is no viscous forces. The fluid flow is steady, and also the flow is irrotational, means the particles do not rotate about its axis. Then we can say it's an ideal fluid. Then we can think, what do you mean by steady flow? The fluid velocity at a point do not change with time. The fluid particle may have a different velocity at some other point. In steady flow, all the particles passing through a given point follow the same path and hence a unique line of flow. The line or path is called the streamline. The streamlines do not intersect. For if they do so, any particles at the point of intersection can move in either directions. Consequently, the flow cannot be said to be steady. So be careful, no streamlines intersect. Then what do you mean by laminar flow? In which fluids particles move along well-defined streamlines which are straight and parallel. In laminar flow, the velocities at different points in the fluids are same. In turbulent flow, it is an irregular flow in which the particles moves in zigzag way. Look, the very important concept, the equation of continuity. And we can say the law of conservation of mass in fluid mechanism. It actually reveals the volume flux, the rate of flow, the volume of liquid flowing per second, that is denoted as dV by dt. That is nothing but equal to the area into velocity. If you just compare a tube flow with the different cross sections, we can say A1 V1 should equal to A2 V2. It's a very important concept. Then the Bernoulli's theorem, the very important in our entrance exams. In case of steady flow of incompressible and non-viscous fluid through a tube of non-uniform cross-section, look the figure from the ground level, the two different sections of a tube flow is under consideration at a height h1 and h2. And keep in mind, if we just consider the total energy is a constant, we have to consider the pressure energy, the kinetic energy and the potential energy is a constant. So here the energy per unit volume, we can say P plus half rho V square plus rho GH is a constant. If you just take the energy per unit mass, we have to say as P by rho plus V square by 2 plus GH is equal to constant. But if you have to consider the energy per unit weight, then P by rho G plus V square by 2G plus H is a constant. That means the pressure head plus the velocity head plus the gravitational head is a constant. It's a very important one. And keep in mind, have a lot of applications. The venturimeter, it is used to measure the flow of velocities in an incompressible fluid. We can just go through that concept. Look the figure. See, here cross section, and there the pressure is P0 here, and here the tube, the velocity is V1, the area of cross section is A1, and here the area of cross section is E2, the velocity is V2, and there is a difference in level of H between the liquids and the two tubes. Then we can find the velocity here V1 is equal to A2 into root 2gh by A1 square minus A2 square. We can find V2 also by using this concept. Then the quantity of water flowing is A1 V1 or equal to A2 V2 equal to A1 A2 into root 2gh by A1 square minus A2 square. The speed of efflux, the velocity of efflux, the torusel is low. So in a container, that surface of liquid is at a height h from the bottom, and suppose there is an orifice having area cross section A2 at a depth h from the surface. If that container got of area of cross section A1, then we can say the velocity from the orifice as the very, very important concept as root 2gh by 1 minus A2 by A1 the whole square. But in the usual cases we are using the formula root 2gh. But it is an assumption, as if the orifice area is very much less compared to the area cross section of the container, then we can say A2 very much less than A1, and we carry the formula as a root 2gh. The velocity of efflux is independent of the nature of the liquid, the quantity of liquid in the vessel, and the area of the orifice, if you just take that consideration. Look the concept, the time taken by the liquid to reach the base level. It's a good formula as T is equal to root 2 h minus h by g, and keep in mind the range by considering it as a horizontal projection, as we get the formula as x is equal to v2 into t, and hence we can find it to be as equal to 2 into root small h into capital H minus h. And keep in mind that range becomes maximum when that orifice hole is at a depth of capital H by t. And keep in mind the range will be same if the orifice is at a depth h or capital H minus h. So like the projectile angle, we get the range becomes maximum when angle theta and 90 minus theta, the complementary angles. The same case is here also. Look the another very important concept, the time taken to make the tank empty. The time taken for the level to fall from H to H dash as T is equal to A by A orifice into root 2 by G into root H minus root H dash. If the hole is at the bottom of the tank, the time T to make the tank empty as T is equal to A by A0 into root 2H by G, and have a lot of applications based on the Bernoulli's theorem, the manganese effect, aerofoil, sprayer or atomizer, the blowing off of rooftops in windstorm, pull-in or attraction force by fast-moving trains. And keep in mind, the pressure head plus the velocity head plus the potential is a constant. That means whenever there is a decrease in pressure, there should be increase in velocity. Whenever there should be a decrease in velocity, there should be an increase in pressure. Keep in mind. And we can just go through some problematic situations. Water is filled in a tank to a height of 3 meters. An orifice is made at height 52.5 centimeter from the bottom of tank. The ratio of the cross-sectional area of the orifice and the tank is 0.1. the square of the speed of the liquid coming out from the orifice is. We know the simple concept as we take the value as root of 2gh by 1 minus a2 by a1 the whole square, but we need to find as v square. You just substitute the values and we have to find what is the h. The total height is 3 meter, so 3 minus 52.5 centimeter, so 3 minus 0.525 in meter. So 1 by 2 into 10 into 3 minus 0.525 by 1 minus 0.1 square, you get the answer. A rectangular vessel, when full of water, takes 10 minutes to be emptied through an orifice in its bottom. Then how much time will it take to be emptied when half filled with water? So we can just compare the two situations. So you know the simple formula is T is equal to capital A by A0 into root 2h by g. So you just take the root of h1 by h2. You get the answer. See the next another question. The cylindrical tube of a spray pump has a cross section of 8 centimeters square, one end of which has 40 fine holes, each of area 10 raised to minus 8 meters square. If the liquid flows inside the tube with a speed of 0.215 meter per minute, the speed with which the liquid is ejected through the holes is. So we know the concept as an equation of continuity. A1v1 should equal to A2v2. So for the tube flow, we can say the area is 8 into 10 raised to minus 4. The velocity is 0.15 meter per minute. So by 60, it should be equal to 40 holes are there. So 40 into 10 raised to minus 8 into the velocity as v2. And from that equation, we easily find the velocity with which that liquid flow from the small holes. In a test experiment on a model aeroplane in a wind tunnel, the flow speeds on the upper and the lower surfaces of the wings are 70 and 63 meter per second. Then what is the lift in the wing if its area is 2.5 meters square? But if we just apply that aeroplane is at a height h and apply the Bernoulli's theorem, we can write it the upper and the lower part by using the concept P2 minus P1 is equal to half rho into V1 square minus V2 square. We know the power is pressure is nothing but equal to force by area, and hence we can find the upward force on the wing as F is equal to that P2 minus P1 into A. You can just substitute and you can substitute the given values here. It is given the density of air as 1.3, the V1 as 70 and V2 as 63 and the area of cross section as 2.5. You get the answer. Another question. A container with a square base of side A is filled up to a height h with a liquid. A hole is made at a depth h from the free surface of water. With water acceleration, the container must be accelerated so that the water does not come out. A good logical question. The choices carefully, please look it. And we know V equal to root 2gh. When vessel is accelerated down with an acceleration g, then the pseudo acceleration g will be vertically upward and effective value of g is 0, and hence the water will not flow. So freely falling condition. So that is a very good concept. The viscosity, the internal tangential force which tends to retard the relative motion between the adjacent layers of a tube flow, is called the viscous force. So here suppose in a flow the adjacent layers are separated by a distance of delta y or dy, and suppose one layer that is moves with the velocity vx and another one it is moves with the velocity vx plus delta vx. then we can say the Newton's law of viscous force F is proportional to the area of cross section and the velocity gradient. And keep in mind the velocity gradient is a vector quantity whose direction is perpendicular to the direction of flow. And that proportionality constant is called the coefficient of viscosity, and it depends upon the nature of the fluid and is independent of area or that velocity gradient. And it is expressed in terms of SI unit Poiseuille, in CGS unit as poise. You should know the link between the Poiseuille and poise. As 1 Poiseuille, take the value as 10 poise. Its dimensions are a very important concept. And keep in mind, in case of liquids, viscosity increases with density, while for gases it decreases with increase in density. With a rise in temperature, the viscosity of liquids decreases, while that of gases increases. With increase in pressure, the viscosity of liquids increases, while that of gases is perfectly independent of pressure. And the case is entirely different for water. Keep in mind the very important two relations. Keep in mind the Stokes law. If a small sphere of radius r is moving with the velocity v through a homogeneous stationary medium, the viscous force acting on the sphere is given as 6 pi eta rv. Eta the coefficient of viscosity, r the radius of the sphere, v the terminal velocity. And keep in mind the terminal velocity. When a drop of radius r is moving or coming downward, keep in mind the forces acting on it, the weight vertically downward, the buoyant force upward, and the frictional force, that viscous force in the upward direction. If you just go through it and you get the very important relation for the terminal velocity as 2 by 9 into r square into rho minus sigma by eta into g, and keep in mind rho the density of that drop and sigma that for the fluid under consideration, and see the velocity versus a distance curve for a drop under movement. The Reynolds number is nothing but the inertial force by viscous force and is a constant for a particular flow, and it depends upon the factors as a rho Vd by eta. And based on NCRD, we can say that Reynolds number is said to be less than 1000. We can say it is laminar, greater than 2000 as turbulent, but in between 1000 and 2000 it is a transition region, maybe laminar or turbulent. Look, the profile of the advanced liquid in a tube flow, that we can sense it is a parabola. And keep in mind the layer at the axis moves with the maximum speed, but on the surface it becomes zero. And keep in mind the velocity of flow at a distance y from the axis as v is equal to p by the pressure by 4 eta L into r square minus y square. It is a very important one, and keep in mind that y distance is at a separation from the axis. It's a good relation, a good concept. Again, the Poiseuille's equation. In case of steady flow of liquid of viscosity eta in a capillary tube of length L and radius r under a pressure difference P, the volume of liquid flowing per second is dq by dt equal to pi p r raised to 4 division by 8 eta L. Then we can compare that tube flow with the current through a resistor. And you can just compare that current, the charge flowing per second, as here the quantity of water flowing per second. So the 2T of the potential difference is done by here the pressure, then the resistance, The resistance offered to the liquid flow by the tube is denoted as R. The liquid resistance is 8 eta L by pi R raised to 4. It is a very, very important concept. If you just consider the series combination of two tubes with L1, L2 length, R1, R2 radius, you know the quantity of flowing, the quantity of fluid flowing is a constant. But the pressure differences are different, like potentials in our electricity circuit. So we can write as P is equal to P1 plus P2. But here the volume are constant. So we can write as P is equal to I into R. Then from that we get the concept. The liquid resistance is the sum of the individual contributions. Like that, the parallel combination of two, keep in mind for a parallel combination, the potential is a constant. Like that, here we can say the pressure differences are constant, but the quantity of liquid flowing through each tube, we have to add it together to get the total quantity of water. So based on that concept, we can write as V is equal to V1 plus V2. From that we get the very important concept as R effective, the liquid resistance in a parallel combination of tubes as R1 R2 by R1 plus R2. It is a very good concept. We can move with the very good questions. A ball is thrown vertically upward at a time t is equal to 0. Air resistance is not negligible and the acceleration of free fall is g. The ball reaches a maximum height at a time t equal to capital T and then descends, reaching the terminal speed. Which graph best shows the variation with the time of the acceleration A of the ball? So at first move upward, then coming back and attains that terminal speed. You know, as the ball ascends upward, in addition to weight, the air friction also acts downwards. Hence, the initial magnitude of acceleration will be greater than the magnitude of g. So we can directly give the answer as the third one. An air bubble of radius 1 centimeter rises from the bottom portion through a liquid of density 1.5 gram per cc at a constant speed of 0.25 centimeter per second. If the density of air is neglected, the coefficient of viscosity of the liquid is approximately, the terminal velocity. If the density of air is neglected, we can say as 2 by 9 into r square rho g by eta. And from that you can easily find the value for eta by substituting the value. So you get the answer as 130. Two equal drops of water are falling through air with a steady velocity v. If the drops coalesced, what will be the new velocity? So here we know the terminal velocity is proportional to radius square. So here intuitively its radius is r, but after coalesce it become a bigger one. Because of the volume conservation, we can write as a volume of the bigger one is n times the volume of the smaller one. We can find the radius as is equal to n raised to 1 by 3r. And you can hear the two equal drops, so you just get the capital R value. So for the bigger one, which is proportional to r square, so 2 raised to 1 by 3r the whole square, you get the answer. The velocity of water in a river is 18 km per hour at the surface. If the river is 5 meter deep and the flow is streamlined, find the shearing stress between the horizontal layers of water, assuming the uniform velocity gradient. The viscosity of water is 10 raised to minus 3 Poisson. A good concept. The shearing stress is nothing but equal to force by area. From the Newton's law of viscous force, we can write it is equal to eta into dv by dy. We can easily find the value for dv by dy from the data. Then you get the answer. The surface tension, the force acting per unit length of an imaginary line drawn on the liquid surface. And keep in mind, the direction of force is perpendicular to the line and tangential to the liquid surface. And keep in mind, the surface tension is the force per unit length and is a scalar quantity and is expressed in Newton per meter. Look, some problematic situations. When a needle flows on the liquid surface, so keep in mind that surface tension can be split into two components, and that horizontal components cancel, and hence this weight is balanced by 2t L sine theta. So it is a very important concept. And similarly some other situations. So if the needle is lifted from the liquid surface, so what is the minimum force needed? Mg plus, we have to overcome the force due to the surface tension. So here the two surfaces link, and hence we have to write as 2TL. The required excess for a circular thick ring dipped in and taken out from the liquid. So inner radius is R1, the outer radius is R2. So we can easily find that one. For the inner one as a 2 pi R1 into T, and for outer one as a 2 pi R2 into T. So that is the excess force needed. But for a ring, and there R1 equal to R2, and hence take the value as 4 pi T. For a circular disk, the run of the radius becomes 0, and hence 2 pi RT. The surface energy, the very important concept, it is the work done in increasing the surface area by increase in surface area. And I got the same formula for same dimension for our surface tension. Look the some problematic situations. Work done in formation of a drop of radius R. The area is 4 pi R square into surface tension. But for a bubble, two free surfaces are there. So 2 into 4 pi R square into T. The work done in splitting a big liquid drop of radius R into n small identical drops of radius. Very important 3 sets of equations. 4 pi T into n small r square minus capital R square. 4 pi capital R square T into n raised to 1 by 3 minus 1. Or 4 pi R square T into 1 by small r minus 1 by capital R. And keep in mind, in this process, the temperature of the system decreases as energy gets absorbed during the increase in surface area. So that can be related to the thermodynamic relations. So J into M as delta theta. Keep in mind, AC is the specific heat capacity that we can easily equal to that surface energy as a 4 pi R cube into T into 1 minus 1 by R minus 1 by capital R. A good 1 or 2 problems. PQRS is a rectangular frame of copper wire as shown in figure. The side RS of the frame is movable. If a soft film is formed on it, then what is the diameter of the wire to maintain equilibrium? To maintain equilibrium, so the force of surface tension, it should be equal to the weight. So 2TL should be equal to mg, but we can write that mass is equal to only m into density into g. So we can easily find the value for the radius. So the diameter become double of it, so 1.14 millimeter. A water film is formed in between two parallel wires whose length are 10 cm and placed at a distance of 0.5 cm apart. Find the work done in order to increase the distance between the wires by 1 millimeter. You know the simple concept that work done, it is equal to surface tension into the change in surface area. So we can easily find that value. You get the answer. A big drop is formed by coalescing 1,000 small drops of water what will be the surface energy? What will be the ratio between the total surface energy of the droplets and the surface energy of the bigger drop? What is the surface energy of 1000 droplets? It is easily find 1000 into T into that area. But we can just relate with the bigger one. As a capital R is equal to n raised to 1 by 3r by using the conservation of volume. So we get the smaller radius as a capital R by 10. You get the value for that one. And what is the surface energy for the bigger drop? T into 4 by r square. You can just take the difference. Again, we want to find what is their ratio. You get the answer. A very good concept, the excess pressure. Excess pressure, the difference of pressure between the two sides of the liquid surface is called excess pressure. And keep in mind, if you just consider a concave surface, if you just see the very important concept. See, for a plane surface, the excess pressure between them is 0. But for a concave surface, the outside pressure is greater compared to the inside. So the excess pressure is 2T by R. For a convex surface, it is 2T by R. For a drop, it is 2T by R. For a bubble in air, we can say 4T by R. But bubble in water, it becomes 2T by R. Are very important concepts. See the shape of liquid meniscus, and this is we can just relate with the force of adhesion, that is nothing but the force of interaction between the container, the vessel nature of the container, and also the liquid under consideration. And keep in mind that is acting always perpendicular to the surface, but the force of cohesion, the nature of the liquid, and is acting at an angle 45 degree with respect to the vertical container surface. So it is a very important concept. The magnitude of these two forces will determine the meniscus is become plane or concave or convex. So it is a very important concept. And see the case, the direction of the resultant makes an angle with respect to that adhesive force. It is given as a tan alpha. That is a very important concept. That is Fc sin 135 by Fa plus Fc cos 135. And this is a very important relation. And it will actually decide. Suppose the cohesive force is equal to root 2 times of the adhesive force. In that case, the resultant is acting vertically downward along the surface, and the liquid meniscus must be horizontal. And there we can say the angle of contact, the tangential surface with the vertical surface becomes a 90 degree. Example, the water silver combination. But if Fc is less than root 2 Fa, the tan alpha become positive and alpha angle become acute. The resultant force is directed outside the liquid and the meniscus become concave, and there we can say the angle of contact, it is less than 90 degree. We can quote the example for pure water as 0 degree over ordinary water around 8 degree. But if Fc is greater than root 2 times Fa, the tan alpha become negative and alpha is obtuse. It is a very important concept. The resultant force is directed inside the liquid and the liquid meniscus become convex upward. Look for a mercury glass combination. The angle of contact, the angle between the surface and the tangential drawn on the surface become 136. And keep in mind, if that for a plane surface, it will not wet the surface, but if the angle of contact is less than 90 degree, it will wet the surface. It is a very, very important concept. And keep in mind, the angle of contact does not depend upon the inclination of the solid in the liquid. On increasing the temperature, the angle of contact decreases. For soluble impurities, increases the angle of contact. Partially soluble impurities decreases the angle of contact. Look, the capillarity, it is a very important concept. The capillary rise or descent, it depends upon the nature of the liquid, the container combination. That H can be write as 2t cos theta division by r rho g. The radius of the meniscus, that is given as a small r by cos theta. It is a very important concept. If a capillary tube is dipped into a liquid and tilted at an angle alpha from vertical, then the vertical height of liquid column remains the same, whereas the length of the liquid column L in the tube increases. It is a very important, but the height remains the same. We can just relate that H with the alpha, that L is equal to H by cos alpha. It is a good concept. The Zurin's law, for a given liquid and solid at a given place, we can say H is proportional to 1 by R, or H into R is the capillary height and that radius of the tube are a constant. And keep in mind, in case of a capillary of insufficient length, the liquid will not overflow like a fountain. It rises to the available height by adjusting the meniscus. That is a very important concept. If two bubbles of radii R1 and R2 coalesce isothermally, then the radius of the new bubble will be. So you just consider the number of moles of molecules inside N1 plus N2 should equal to the total one because of the coalesce. So we can write as a P1 V1 plus P2 V2 equal to PV. And for the bubbles, you can write the pressure as a 40 by R1 into the volume. So you just take the answer that R1 cube cancel, we get R1 square. So R square equal to root R1 square plus R2 square. A bubble of air of radius of 0.1 millimeter in water. If the bubble had been formed 10 centimeter below the water surface on a day when the atmospheric pressure was 1.013 into 10 raised to 5 Pascal, then what would have been the total pressure inside the bubble? So we have to use the concept as P atmospheric pressure plus H rho g, that due to the liquid column, plus the excess pressure. So you get the answer. A good concept, a hollow sphere which has a small hole in its bottom is immersed in water to a depth of 30 centimeter before any water enters into it. If the surface tension of the water is 75 dynes per centimeter, then find the radius of the hole in it. It is a very, very, very important concept. By using the capillary concept, you can say the radius of the hole is 2t division by h dg. A good concept to keep in mind. A U-tube is supported with its lens and is partially filled with water. If the internal diameter of the limbs are 1 into 10 raised to minus 2 and 1 into 10 raised to minus 4 respectively, what will be the difference in height of water in the two limbs? So you just find the value of H1 and H2 and take the difference. Two identical soap bubbles, each of radius r and of the same surface tension T, combined to form a new soap bubble of radius capital R. The two bubbles contain air at the same temperature. Then find the surface tension T of the soap solution in terms of atmospheric pressure, radius, and we have to assume as isothermal process. So we can easily write as the concept as, and see the case PV as a constant. So we can write the concept here, 2 into PV is equal to P dash V dash. So we can write that the pressure as atmospheric pressure plus the excess pressure into the volume. So everything become easy. So The students, it's a very important concept. We actually done a previous video regarding the pressure, density, and also Archimedes principle. From a fluid, say, we can write minimum 2 to 3 questions for NEET or KEAM entrance examination. So try to do maximum MCQs. God bless you. Take care.